We're recording again. Now we're doing a discussion of the section 4.4 notes, pages 1, 2, and 3 is what we hope to cover. So what we're going to do is we're going to go to our graphing calculator. We're going to do a little exploration. We're going to put e to the x power under y1 and the derivative e to the x under y2. And we're going to try to see what happens when we do that. Then we're going to fill all this stuff here in just a little bit. So if we go to our calculator, go to y equals, and just do e to the x. Now e is second ln x. And what I'm going to do is I'm going to, y2 is going to be the derivative of y1. Now you can replace y1 with e to the x. That's how I have it in the notes here. But you can just keep that as y1 if you want, or e to the x, I don't really care. But we're going to make it darker though, however. So to make it darker, you just go to the left, and you just hit enter, and you see that makes it a thicker line. And I'm going to graph this under the standard window. Excuse me. And notice how the derivative just traced the original. So again, so you guys are with me. y1 is e to the x. So let me go and clear it. Second ln x. y2 is this. That's alpha window, so how you call it the derivative. That's option 3. Actually, I'll just clear it. What the heck? So alpha window, option 3, x. And here you could put e to the x or just put alpha trace y1. You'll know to take where y1 is. You make that x equals x. And I want to make that darker. So go all the way to the left and just hit enter once. Now, if you hit it multiple times, then it changes it like this. It makes it like an inequality. Just keep hitting enter until you cycle through all the options. It also does like dotted lines and then back to regular line, regular curve, and then fill in. And go zoom 6 to graph in the standard window. You have e to the x and you have that. And if you hit the trace button, we see that the derivative e to the x is itself. That's weird. It's itself. So the derivative e to the x is itself. Just so you know, sometimes e to the x is written like this. For those who actually do like computer programming, like R or Python, I do some of the fun stuff I do with sports. They tend to write exp, or if you do that like in a Desmos, if you write exp, it knows to do e, the number e. But anyway, the derivative of that is itself. Or you could do a chain rule with this, right? Like if I do a derivative e to the x squared plus 2, that's what that means, right? That's e to the x squared plus 2. But a chain rule times 2x. So keep in mind that chain rule is still applicable here. Actually, chain rule is always applicable. It doesn't go away. There's no exceptions to it. You always got to do chain rule. Even for basic stuff like x squared, we do chain rule. Of course we do. You just don't show it. But, you know, because the derivative x itself is 1. So you don't really care about that, right? But so let's actually kind of keep going here. By the way, there's a formal proof for this. I did the formal proof in the video that you guys watch over the weekend. I didn't want to do that for class in the interest of time, but it's at the end of the notes. So example 1 is pretty easy. That's just going to be e to the 5x, but times 5. So you're doing chain rule. Or for example 2, it's going to be e to the x squared plus 3x times the derivative of x squared plus 3x, which is 2x plus 3. And then plus the derivative of 5e. Now 5e, anyone want to tell me what you think that derivative will be? What would be the derivative of 5e?
5.
0.
It would be 0 actually. Because what is e? Is it a variable or a number?
It's a number.
Exactly. It's a constant. It's just a 0. That's to say be careful there. So it's just this right here. You can put the plus 0 if you want. So yeah, e is just a number. So don't worry about it. Now remember, e to the x is an exponential function because your input's an exponent, right? X to the n is a power function. Keep that in mind as well. And this will hopefully clear up some confusion that you might see regarding this stuff. Let's look at the bottom of that table. Let me change colors, something more appropriate. Like x cubed. What's the root of x cubed? We know it's 3x squared, right? Because that's a power function. But what about 3 to the x?
3x, x minus 1?
Nope. That's a total misconception. Yes, I can see why people would say that. People would think, oh yeah, move the x to the front and do that. The problem here is that that is not a power function. This only works when you have x in the bottom raised to some power. This is why we're going to have to do a formal proof of this eventually, so that you don't make that you don't confuse those things. Like this, yeah, absolutely. You move the n to the front. This only works when the exponent here is a constant. When you have like x to the third power, for example. But when the exponent is not a constant, when the exponent is actually a variable, this is an exponential function. So here we actually have to do something kind of unique. In fact, the answer for this is 3 to the x times the natural log of 3. I'm going to explain this rule to you guys in just a minute. But whenever you have a exponential function, now e to the x was an exponential function, and we already saw graphically that was just e to the x. But what if the base is not e? What do we do then? And that's what we did over here. I'm going to explain why I have to put the ln in just a little bit. But do not do this. That's really bad. And I don't blame you guys that someone said that. Trust me, a lot of people think that. But that's not a true thing. That's because it's not a power function. And there's actually a formal proof for power functions, which I hope to try to get to in this video today. Sorry, in this lesson today, which I'm doing a video of anyway. Okay, let's keep moving. So let's do a little demo here. So I can prove to you why the derivative of 3 to the x was 3 to the x times natural log of 3. Where again, this was 3x squared. And the difference between the two, that was a power function for x cubed, but 3 to the x was an exponential function. So let's do a little, let's do another demo. Let's do 2 to the x instead of e to the x. So I'll go back to my calculator. Go and clear my drawings for now. Let's make that 2 to the x. So 2 raised to the x power. And I'll keep y2 alone, and I'll keep it thick. Graph in the standard window. There's 2 to the x. And notice how that thick curve is a little different now, right? It looks a little different. So going back to my notes again, add this for 2 to the x. But then for the derivative, it looked like this. It looked a little different. And don't worry about sequential mode. I'm not sure what that means. Actually, maybe I do need to worry about that. I don't know. We'll see. But let's do this again. But now let's add this to our graphs. So I'm going to go to Y3. I'm going to do alpha trace Y2 divided by alpha trace Y1. Turn off these bad boys here. Graph, I'm going to just graph the standard. Okay, I see why we should be in Zoom 4, so you can see a little better what's going on. Let me go to Zoom 4. Okay. Now, if I move the cursor, okay, now I see why Ms. Blanford said to be in decimal mode. Got it. Every tick mark is still worth 1 unit. But see, notice that when I go up and down, it goes up by a decimal. Okay. So where is this graph located? This graph is located at y equals 0.7. Or if it trace, I mean, close enough. It says 0.693. So actually, that's what it is technically. It's y equals 0.693. So apparently, y2 is my derivative, and y1 is the original. So when the ratio of the derivative and the original is a constant. In fact, what if you do the natural log of 2? .693. Let me go back to my graph again. Trace 0.693. So what this is telling me is that the derivative of 2 to the x, the derivative of 2 to the x divided by 2 to the x itself equals some constant, in this case, natural log of 2. So the derivative of 2 to the x is 2 to the x times natural log of 2. Now, why didn't we do that for e to the x? We did. I just didn't show it to you guys. Anyone want to tell me what natural log of e is? This is why I probably should have done the log review with you guys, if you guys may have forgotten from last year. It's 1. Natural log of e is 1. That's because natural log is base e. And whenever the base and your input are the same, it just equals 1. So actually, we did do that. We just didn't show it. So the derivative of all exponential functions is going to be itself times natural log of its base. So let me actually write that in the text box. Let me actually do a little text box maybe over here. Make it nice. Oh, come on. The derivative of an exponential function, i.e. like 2 raised to the x, is the function itself times ln of the base. That's always true. So if you want to do for ETX, go ahead. Derivative ETX times ln e, but ln e is 1 anyway. I'm not going to fault you for doing that, just you don't need to. But for everything else that's not e, like say 3 to the x, 4 to the x, or 5 to the x, or whatever, derivative 5 to the x is 5 to the x. times ln 5. So you always got to do an ln thing. So that was kind of the point of that demonstration, to show that to you guys. So in this case, again, we had this as 2 to the x, the derivative. Okay, let me be consistent. I think I did green originally. Oh, goodness. Okay, a little better there. That's 2 to the x. That's the derivative. And when I graphed this, it was just a horizontal line. So the derivative of 2 to the x is 2 to the x times ln of 2. Again, what's happening here was at 0.693. So y2 was y1 times 0.693. And again, y1 was 2 to the x, and 0.693 is ln 2. Hopefully that makes it more clear now. And y2 was just the derivative d dx of 2 to the x, right? So hopefully we're okay with all that. Now we're going to do some problems. There is actually a formal proof of it. I don't know if I want to do that right now. Maybe I'll save that for next week. I just want to make sure you guys can do your homework. So let's skip this part for now. It's a little bit mind-bending. I think it might be help to actually do some problems with this first. We'll come do that proof later. It's a good proof. I love this proof a lot. It's not anything I'm going to assess you like, oh, here you have to do the proof on an AP Calc. They don't do proofs on AP exams either, but or this AP exam. But it's a cool proof. But we'll skip for now. But again, the derivative of anything raised to the x power is a to the x times natural log of a. And you do have to be mindful that if your exponent is not plain old x, it says like maybe it's like x squared or some other stuff. Don't forget to do a chain rule with that. So a to the u times natural log of a. But then you got to do your derivative with respect to x. And we're going to practice this in just a second. But all this right here, we'll skip for now. I'll do this with you guys on Tuesday next week. Because after this, then we're going to do 5-1 next week. But 5-1, I could probably do in a day and a half, so I don't need 2 full days for it. And that will be our last section of 2020. And then we go into 2021 after break. And hopefully we don't have crazy stuff like we did this year. Anyway, let's go to examples 3, 4, 5. So this one here is really simple. Let me just reposition this a little bit. That's just going to be y prime, just going to be 10 to the x times natural log of 10. That's all. Done. Here, I'm not sure why that's there. It looks like that's a typo. Cross it off. Here, the derivative is going to be 5 secant x, but then times derivative secant x. Oh, sorry, and natural log 5, my bad. Times natural log of 5, and then times derivative secant x. Because you got to do a chain rule, right? So 5 secant x times natural log 5, and that's going to be secant x tan x. Yeah. Easy enough.
Mr. E,
Hmm?
could you combine the 5 to the secant x with secant x so then the 2 secant x's cancel out?
No, because that's an exponent.
But if the exponent and the base are the same, don't they cancel?
No.
Oh.
No,
Oh,
think
no,
about
never mind.
what if you have like x squared times 2? I can't cross off those 2's, right? You don't want to do that. Because remember, if you're multiplying by something, the inverse multiplication is division. Yeah, if I had x squared over 2, sure, cross off those 2's. But no, you don't want to do that. Now, where things get a little dicey is with the logs. If I have log base 5 of 5 to the x power, yeah, then those 5's would cancel. Now you just get x. And we're going to hit up logs in just a little bit. Let's look at this next one here. That derivative is going to be is what it is. Times ln 7. Notice I keep forgetting to do that. So I got to remember that. And then times the derivative of x cubed plus sine x. Okay. So if I finish this off, I get 7 x cubed plus sine x times natural log of 7. Gosh, let me do that again. That was really messy. Sine x times natural log of 7 times 3x squared plus cos x. Again, you can always use Desmos, not Desmos, sorry, your TI4 calculator to verify this. You always plug in the original under y1, ddx of y1 and y2, and for y3, what do you get by hand for the derivative? Make sure y2 and y3 are the same. Okay. I know we got a few minutes left, but I think I could at least talk a little about logs with you guys, so it's not too bad. So what's going on here with derivative logs? Well, derivative ln x, sorry, y equals ln x. Hopefully you guys remember that's y equals log base cx. Also, hopefully remember that it's also the same thing as saying this. X equals e to the y power. Remember, the whole essence of a log is isolate exponents. Like x equals b to the y power. If x equals b to the y power and you want to isolate y, you write as a log. This is why we had logs in the first place. You might remember back in the day, y equals b to the x, when you started learning about exponential growth and decay. And then when we learned about inverse functions, you switched to x and y. And then we had to figure out a way to isolate y. That's why we had logs, just so you know. So this right here is the whole essence of logs. I do worry about the current algebra or the current pre-calculus students who had to learn this in the pandemic. We'll see how well they know it when they do calculus next year. But you know, you guys saw some algebra 2 years ago. Hopefully, you got reinforced well in pre-calculus. But when you do this derivative, we're going to do implicit. So I take the derivative of both sides with respect to x. And I got to do d dx of e to the y. And actually, let me just show you that I'm doing this here. I know the left side's 1, but let me just show you that I'm doing d dx of both sides. So yes, so that's 1. And that's going to be e to the y times dy over dx. Now, if I isolate dy over dx, I get 1 over e to the y. Well, what's e to the y equal to? X. And believe it or not, that's actually your answer. That's it. So I didn't lie, but this turns out to be easy. The derivative ln x is 1 over x. That's all. The assumption, however, is that your x is greater than 0. You can't log negative numbers, or you can't log 0. That's because of the essence of where logs came from in the first place. Like if you have a base that's positive, how can you raise b to some power and make it negative, right? That'd be impossible. So you have to make sure that your x stays positive. Or you can do a chain rule with this, 1 over u, but then times d over dx. And granted that u is bigger than 0. Okay, so I think we could just squeeze in a couple examples. And then I think what I'll do is I'll probably have to finish off these portion of the notes on Tuesday. I won't make a new video. I think I'll just finish it off, whatever I don't get to on Tuesday. But at least pages 4 and 5, they actually cover more exponential stuff. So I think that's fine. So anyway, and we obviously could do more practice of this on Tuesday. So let's just apply this stuff here really quickly. Be done with these notes. So for this one here, this will be just 1 over 7x times derivative of 7x, which actually is kind of interesting. You do 1 over 7x times derivative of 7x, which is 7. You get back to 1 over x. It's kind of weird. Even though we didn't do ln x, we did ln of 7x, and I did my chain rule, I still got 1 over x. Why would that make sense? Remember your property of logs. When you have a product, you can break it up like this. And if I do my derivative, that's going to be 0, and that's going to be 1 over x. So that's why it actually doesn't matter that we had somebody multiply the x here. You still got 1 over x anyway. Now, of course, if you have like ln of x squared or ln of x cubed, then yeah, you're going to have something else going on there. But in that case, it was just 1 over x. In the interest of time, I think I will definitely stop here. And I think I'm going to make an adjustment to your homework too. I don't think I'm going to do 1 through 27 odd in the textbook. I think I'll just do 1 through 13 odd. So I'm going to make an adjustment right now. So what I'll do is I'll pick this stuff up again. I'll do that at the top of page 2, which I didn't quite get to. I'll do that on Tuesday. I'll do all this stuff on Tuesday as well. And this is actually a formal proof of the power rule now. And you'll see why that power only works for x raised to some power, not something raised to the x power. For something raised to the x power, you just got to do what we've been talking about today. Like, like e to the x, e to the x, then times ln e, or 2 to the x times ln 2 and whatnot. But ln e is 1, so don't worry about that. But ln 2, you have to write. Yeah. And I'll make adjustments to the homework, so you don't have to do as many textbook problems. So, but the video you'll still watch on pages 4 and 5. That's already set. So I think what we'll do is homework won't be, I think, as rigorous, and we'll probably do a little bit more work on 4.3 and 4.4 on Tuesday to make sure you guys got it. And then I'll kind of introduce 5.1. Maybe do a video on 5.1 between Tuesday and Thursday next week, and then do more 5.1 on Thursday. And then we actually have a short test on the Tuesday after that. And then the Thursday, I wish I could put the test on Thursday for you guys right before break, but we're not allowed to do that. So we'll just do some, I don't know, other work. I'll figure it out. But I'll make sure I'll give you guys some review materials also next week, because yeah, the special's gonna be over in the blink of an eye. And hopefully we can say the same about the pandemic too. So anyway, let me stop the recording.